While densitometry is an archaic form of image analysis, I have found that some of the concepts embodied in densitometry to be helpful in understanding digital image formation, especially when one considers radiation exposure. To perform a densitometric analysis, we start with a device called a penetrometer. A penetrometer consists of a block of aluminum that has steps cut into it. Each step is 1/8 of an inch thicker than the previous step. An alternate name for a penetrometer is a step wedge. When it is radiographed, the penetrometer will cast an image like the one below. Each step is progressively lighter as the aluminum becomes thicker. For this presentation, I will number the steps from 1 to 11, designated the thinnest step, or the darkest one, as step 1, and the thickest step as step number 11. The second piece of equipment needed is a densitometer. The densitometer is a device used to measure density in a small area of a radiographic film image. The read arm is here. The film is placed in the space between the read arm and the body of the densitometer. Press the read button and the log density for the step is displayed here. Repeat this operation 11 more times and you will have the data necessary to produce a densitometric curve of the penetrometer image. Densitometric curves were extremely useful when one wanted to evaluate the effects of technical changes such as MAS, KVP, collimation, etc. on a radiographic image. Generally, curves demonstrated the effects of technical changes on photographic properties. To produce an H&D graph, you need graph paper specifically designed for the purpose. The y-axis ranges from 0 to 4 log density units, changing by 1/110th of a log density number for each line. The x-axis runs from right to left, with each line representing the steps from 1 to 11, corresponding to the penetrometer image. Now is the time to graph the data generated by the densitometer. The blue curve is a typical H&D curve, and it has a typical S shape. The middle portion of the curve is where there is enough density change from step to step to make the steps visible. The upper portion of the curve plateaus off and changes between the steps become much more difficult to see as they range from dark gray to black. Densities in the lower portion of the curve are difficult to visualize for the opposite reason. They vary from white to light gray and are not easily seen by the human eye or by a computer analyzing the image for the purpose of image correction. This is a representative image of what the step wedge image that produced this curve looks like. Notice how the steps in the middle of the image are easily seen and the steps on each end are not readily apparent. The parts of the H&D curve have a definite anatomy, and it's helpful to have a basic knowledge of this anatomy. To begin, let's draw the curve. This is the highest point on the curve. It is called Dmax for maximum density. On an X-ray film, it represents the point where all the available silver bromide is converted to pure metallic silver. For modern X-ray film, all manufacturers set the Dmax value to about 3 log density units. This was an acceptable level of black and kept the cost of X-ray film down. For a digital image, there is no silver involved. The radiation amount is measured on a per pixel basis, and a white to black level is associated with the pixel or group of pixels representing the step. If there is a Dmax, it makes sense that there be a Dmin point. The Dmin point is on the modern X-ray film is found to be a minimum of 0.2 log density units. This is caused by the fact that all X-ray film had a slight blue tint added to the film. In addition to the tint, there was some fog caused by scatter radiation hitting the low-density areas of the film. The D-min point was also called the gross fog level. Next, we have the shoulder of the curve. This is the area where contrast drops off and where all of the silver in the emulsion is converted to pure metallic silver. The toe is where radiation levels are sufficient to significantly affect the silver bromide crystals on the film. The straight line portion of the curve represents the piece that form the image on the film. There is sufficient change in radiographic density to demonstrate anatomy with similar part densities or thicknesses. Here is how the penetrometer would be oriented relative to the curve, with thickest step to the left of the curve. If you haven't yet figured it out, the steepness or slope of the curve indicates the contrast of the image. In this first curve, note the difference in density between steps 5 and 6 is 0.65 log density units. Here is a second curve, and it is obviously steeper than the first. If we measure the log density difference between steps 5 and 6, we can see that the difference between steps 5 and 6 has increased to 0.80 log density units. This represents a higher contrast measurement, contrast being defined as the difference in density between adjacent structures on an image. Now, using the previous example, let us deduce the relative contrast for a third curve. What do you think the contrast of the third curve is relative to the previous two? If you guess the curve has a contrast level lower than the previous two, you're correct. It does indeed have less slope. While the curve's slope indicates contrast, the position of the curve determines the average curve density. Contrast and density can be altered independent of one another by manipulation of kVp, MAS, or other radiographic variable. First, let's draw a reference curve. If we draw a second curve to the right of the first, the curve would indicate an exposure with less density than the first. And this curve indicates an exposure with more density than the first. Note that the steps at every level are darker than the first curve. Just to prove the density has changed and not contrast, I'll draw a dotted line parallel to the slope of the right curve. As the line moves across to the other curve, note that the dotted line maintains the same slope as the straight line portion of the curve, indicating the contrast remained constant even though density changed. Here is where I will attempt to equate digital and analog film screen radiography. In reality, we can't generate an H&D curve from a digital image, so we need to make some educated guesses as to how the two systems are related. To make our comparison, the first thing we must do is to shrink the graph paper. Because digital plates can record a much larger range of radiation intensities compared to film screen systems. Additionally, due to image post-processing and correction, this curve can produce an acceptable image over a wider range of technical factors. The hypothetical H&D curve looks something like this. Note that it extends above and below the film screen H&D curve, and there is not a drop-off or density change at the beginning or the end of the curve. There is enough density difference along its entire length that structures can be imaged if density is corrected by the computer. In a film screen image, this amount of radiation at the top of the curve would display as uniformly black. But thanks to the process of computer image correction, this image can be saved. There is enough contrast visible between the steps for the anatomy to be distinguished by the computer, and the density is reduced to acceptable levels using an image correction algorithm. There is less leeway available below the acceptable range because the computer needs density data to reconstruct the image, and the under-range images don't supply sufficient data. The image is grainy in appearance or suffers from quantum model. Since quantum model is a non-geometric change, it degrades visibility of detail or contrast resolution. The mid-portion of the curve represents the sweet spot for exposures, an image that displays a balance between radiation dose and image quality. Let's compare three images of the foot and speculate by their relative position on the hypothetical curve. The first image is a dorsal plantar projection of the foot. This image is calculated to have an LGM value of 1.9, the bottom of the acceptable exposure range set by AGFA. The radiograph on the right is just above proper exposure range. The image quality has been corrected by image post-processing. The image is acceptable except for the fact it was not masked properly. Also, the radiographer used 4 times the radiation dose necessary to produce a quality image. The image on the left has 2 times underexposed and suffers from excess quantum model. The loss of image fidelity is not apparent because this monitor is not up to the standard of a radiologist monitor. Let's now position these images relative to their position on the hypothetical curve. The middle image appears at the confluence of the film screen and hypothetical curves. The image to the right is overexposed and appears slightly higher than the proper exposure on the curve. If it were a film screen exposure, it would be grossly overexposed, very dark and unreadable. But due to image correction algorithms used by the computer, it is made acceptable by shifting window width and level. There is enough contrast for the computer to distinguish the various structures. The image to the left is very similar to the reference image, but there is not enough data to fully reconstruct it. To summarize, for the overexposed image, there is less quantum model. The problem being this is achieved with excess patient radiation dose. Due to excess scatter radiation reaching the imaging plate, the computer didn't properly mask the final image. This problem can be rectified by manually adjusting the mask. A repeat exposure is not necessary, but a competent radiographer would recognize the overexposure and make proper adjustment of technique for future exams. For the 2 times underexposed radiograph, there is not enough radiation reaching the imaging plate, and the result is quantum model. I'd recommend a repeat exposure, especially if fine visibility of detail is necessary for the diagnosis. Let's compare some images where the exposure defect is not correctable and obvious. Again, the middle exposure is correct and in an acceptable exposure range. For the right exposure, the MAS has been increased to the point to where the computer cannot correct the excess radiation. If we try to correct the exposure manually using window width and level manipulation, it is no use. The overexposed pixels remain washed out and dark. To achieve this effect, the radiograph was overexposed by a factor of 16 times. This exposure has been decreased to the point where quantum model is apparent regardless of your monitor's resolution and image enhancement abilities. Note that this exposure uses 8 times less radiation than the reference exposure. When we overlay these images onto the hypothetical H&D curve, the reason for their appearance becomes obvious. The middle image is again set to the sweet spot of the exposure line and acts as a reference exposure for the other 2. This radiograph was underexposed to the point where the loss of information is obvious. The image extends below the ability of the imaging plate to measure radiation exposure to these pixels. The right exposure, or the overexposed one, on the very top of the hypothetical H&D curve. The computer had no choice but to display these pixels as dark gray or black, regardless of their true density value. Let's take a closer look at the unacceptable images. First, the underexposed image. The radiation density in the tarsal metatarsal area is so low that the computer was unable to reconstruct the data. The image appears underpenetrated, but this is not the case. There is too little radiation coverage and the computer cannot reconstruct the image. It cannot separate image from noise. The only salvation for this image is to repeat it using more MAS. In the overexposed image, the pixels in the thinner portion of the foot, the phalanges, are no longer correctable. There is not enough contrast from one portion of the phalanges to another for the computer to distinguish the density difference correctly. I call this effect density saturation. This exposure needs to be repeated. The MAS should be reduced by a factor of 16 times. In addition to the overexposure problem, the image also suffers from a masking problem. The scatter radiation in the image periphery is so great the computer is unable to mask the image properly. The bottom line is the patient received too much radiation to produce a diagnostic image. To sum up, digital imaging systems require as much attention to proper technique as film screen counterparts. Their margin of error is greater, but that is no excuse for a radiographer to ignore proper technique selection. Digital plates are more sensitive to radiation than film screen systems. It is estimated that the lowest radiation dose that can be recorded by film screen technology is about 2 to 10 microsieverts of radiation. A DR technology digital plate is estimated to be sensitive down to 3/100ths of a microsievert, and the CR plates fall somewhere between DR and film screen technologies in their minimum sensitivity. Digital plates can record a greater range of exposure levels than can film screen cassettes. About 2 times lower than film screen systems, and about 4 to 16 times greater than film screen technologies. The large exposure range is responsible for dose creep. This is where a radiographer uses more radiation than is necessary to assure an acceptable image. All images must be evaluated using manufacturer's exposure guidelines as a touchstone for technique selection. Thank you for your attention. This will end my presentation.